Hello everyone, welcome back. My name is Mr. Cobalt, and in this video we're going to go over how to determine basically the molality of H plus ions in solution when you're given a weak acid. So let's get into this. So in this problem we're given that weak acids are only partially ionized in aqueous solutions. Given a 0.5 molal solution of HA, which is your generic formula for a weak acid, with a freezing point of negative 1.05 degrees Celsius, calculate the molality of H plus. So what we're given here is we're given 0.5 molal solution. So this is kind of like molarity, right? So if you're given the molarity of a weak acid, right, that is not going to be the same as the molarity of the H plus in solution, because not all of the molecules of your HA are going to ionize into H plus and A minus, which is your generic anion. So we can't assume that the amount of H plus in solution is 0.5 molar, because it only partially ionizes. If this was a strong acid, then it would 100% ionize, and the molality of your H plus would be the same as your given solution, the molality of the solution. So in this case, we need to figure out the molality of the H plus. So what we need to find here is your Van 't Hoff factor, represented by the I. So I is the Van 't Hoff factor. I is that number that basically tells you how many particles do you have in solution per 1 unit of whatever it is you dissolve. So that will help us out, because the HA as a weak acid is going to be somewhere between 1 and 2. If this was like sugar, right, which doesn't dissociate or ionize in water, then the Van 't Hoff factor would be 1, right? Because for every 1 molecule of sugar, you get 1 particle dissolved in water. If this weak acid, instead of being a weak acid, if it was a strong acid, that means it would totally ionize in water. So that way, from 1 molecule of the acid, you would get 2 ions or 2 particles in water. So the Van 't Hoff factor would be 2. But in this case, since the weak acid only partially ionizes in water, then that means it's going to fall somewhere between 1 and 2, and we have to figure that out. So using the information they gave us a freezing point depression of 1.05 degrees Celsius. We know that the freezing point of pure water is 0 degrees Celsius. So the change in the freezing point is that of 1.05 degrees Celsius, right? So we got that in our for equation. We have the molality of the solution, 0.5, and we have the Kf for water, which is 1.86 degrees Celsius per molality. So all we have to do is plug it into the equation, solve for the Van 't Hoff factor, which is I. So here we have delta Tf equal to I molality Kf. Solve for I, and we get I is equal to the change in the freezing point temperature divided by the molality divided by the freezing point depression constant. So we plug everything in. The delta Tf is going to be a positive change, right? So the change is going to be 1.05. The negative just means that decreased by that much, but the change is going to be a positive value. So here it's going to be 1.05 for the change divided by the molality, which is 0.5 molals, right? This is degrees Celsius. and this is multiplied by Kf, which is 1.86, 1.86, and that's degrees Celsius per molal. So here we have molals cancel out, degrees Celsius cancel out, so we have a unitless number, which is what we would expect for our Van 't Hoff factor. And when we calculate this, we get 1.1290. So what does this mean? It means that for every one of the weak acid molecules that we put into solution, we get out 1.129 particles, right? So again, as we figured, it would be between 1 and 2, right? So it's a little bit higher than 1, not quite 2. So that means for every one of the particles we dissolve of our HA, our weak acid, we're getting an extra 0.129 added. So we start with one molecule and end up with 1.1290 particles. That means we gained 0.1290 amount. That has to be due to the fact that that's the amount that had dissociated, or in this case, ionized in water. So if it didn't ionize at all, it should be 1. Our Van 't Hoff factor should be 1. So for every one particle we put in water, we get one particle that's dissolved in the water. In this case, for every one unit of the HA that we dissolve in water, we get out an extra, we get 1.129 of those particles. So that means we gain an extra 1.290. That has to be due to the H plus, right? So if you think about it this way, so we have our HA is going to dissociate or ionize into H plus plus A minus. So if we take one of these, that means that one of these is going to break apart into 1.1290 of these two added together. So these two, so one of these is going to give rise to 1.1290 of these. So if it was just the HA, right, if it was just HA, then the 1 would stay a 1. But because this dissociates a little bit, we get that extra 0.1290 added on top, right? So that's what we're dealing with here. So we have, excuse me. So what we need to do is we take this 1.9129 or 1.129 factor and we multiply it by the given molality. And so when we do that, we get 0.5 molal. Multiply that by the 1.1290, 1.1290, and we get 0.5645. So that's going to give us 0.56. Let me double check. 45 molal. And so you can see that we started out with 0.5 molal, And when we multiply that by this factor here, we get 0.5645 molal. And you can see that we got a higher molal. So the difference here must be due to the dissociation that occurred here. So that would due to the extra H plus we have. If it wasn't like that, then of course HA would be 1 to 1, but we get this value here. So the extra added must be due to the extra that was created by the dissociation or ionization, so H plus. So if we subtract 0.5 from 0.5645, 0.5, that gives us 0.0645. Or if we round to 1 sig fig, since we have 1 sig fig here and we have 3 sig figs here, right? So we multiplied, divided, we should have 1 sig fig here for our answer here, but we kept the extra digits. So then here, when we multiply, we only got 1 sig fig. So then the molality of H plus should be 0.06 molal. Again, another way you could have done it is, since we know that the extra here must be due to the ionization of that fraction of our HA that we have in solution, then we could just take this extra amount here and multiply that by the original molality, and then that should give us the molality of the H plus. So if we take that, if we take 0.5, multiply that by 0.1290, again, we get this value here, 0.0645. And so that, ladies and gentlemen, is how you solve this problem. I hope this is helpful. If you found this helpful, if you enjoyed this video in any way, then please, by all means, like the video, share the video, hit that like button over there somewhere. Also, make sure you do me a favor, subscribe to my channel, hit that notification bell right up there somewhere. And when you do that, make sure you click all so you'll be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a problem or a question you need help with or a topic that you would like me to cover, put that down in the comment section. I would be more than happy to do that for you. Thanks for joining me and have a great day.